Dear students, good morning. Today we are going to learn threaded binary trace in fourth unit. So in the fourth unit, these are all the contents already completed in previous classes: introduction, terminologies, representation of trace, binary trace, properties of binary trace, binary tree representations, binary tree traversal, pre-order, in-order and post-order traversals. So today we need to discuss threads, threaded binary trace. All of you, threads and threaded binary trace. So small topics. Maybe he will ask in end examinations, what is thread? How many ways to represent threaded binary trace? Explain with an example. Clear all of you? Then maybe he will ask on 6 marks or 7 marks question. So simple and easy to learn. Okay, it is a simple question. It is also easy to learn. Okay, all of you. Then the today topic is threaded binary trace, threads and threaded binary trace. So then these are all the introduction of the tree. So what is a tree? Tree is a nonlinear data structure which organizes data in hierarchical structure, and this is a recursive definition. Am I right? Another one more definition: data structure is a collection of data. The tree data structure is a collection of data which is organized in hierarchical structure recursively. So this is the general tree example for general tree. This is an example for general tree. So any number of nodes. The tree contains how many nodes? Here 11 nodes. How many edges? N minus 1 edges. That is 10 edges. So these are the terminologies. Root, which is the starting node, that is called root node. Edge, so this is a connection between one node from another node, one node to another node, that is called edge. Here parent node, who nodes having child nodes, that is called parent node. Then childs, so then parent node having childs. For example, A is the parent node, B and C are the childs of A. So then B, D, E, F, these are the childs of children of B. GH also children of C. I is a children of E. K is a children of G. Yes, children of G. K is a child of G. Clear all of you? Siblings. So for example, here B, C are the siblings of A. D, E, F are the siblings of B. GH are the siblings of C. I, J are the siblings of E. K is the sibling of G. Leaf nodes, who are the final nodes? Then there is no connections left to right. Those are called leaf nodes. D, I, J, E, K, H. These are the leaf nodes in this tree. Internal nodes, what are the internal nodes? Then A, B, C, E, G. These are the internal nodes. These are the internal nodes. These having some child nodes. That's why those are called internal nodes. H is not an internal node, K is not an internal node, F is not a, J is not a, I and D are the not internal nodes. Okay, those are the leaf nodes, final nodes. Then degree. So degree of tree. So then degree of B is 3. Here 1, 2, 3. Yes. So degree of F is 0. Yes, all of you, degree of F is 0. Degree of B is, how many elements are there? How many nodes? 3 nodes. That is degree of B. B having how many nodes? 3 nodes. F having how many nodes? 0. Then A having how many nodes? Then 10 nodes. Clear? That is the degree of B. Clear all of you? The next one is, next A having 2 nodes. A having 2 nodes. That is the degree of A. Clear all of you? Degree of tree. Next one, levels. Then this is the 0 level. This is 1 level, 2 level, 3 level. How many levels in this tree? 3 levels. Clear? So total 4 levels, but 0 here, starting with 0. So then how many levels? 4 levels. Next one, height of the tree. Same levels, total levels of the tree equal to height of the tree. Here simply, here 0 level. Clear? Height equal to 0. Next one is one first level, second level, and third level. Height of this tree is 3. Height of this tree is 3. Height of this tree is 3. Next one is the depth of the tree. Depth of the tree. Here A. So here C. Then here depth of the A is 0. Depth of the B is 1. Next one, depth of the K is 3. Here simply like levels of the high levels of the 3. Here level 0, level 1, level 2, level 3. Reverse. Here depth 0, depth 1, depth 2, depth 3. Clear all of you? So this is the reverse of so levels. Reverse of levels. Clear all of you? Then height equal to 3. Clear. Here 0, 1, 2, 3. Next one is the depth. This is depth 0, 1, 2, 3. Clear? Next one is the path. Here simple I want to reach from J to J, A to J. Then here A, then process B, then process C, then process J. This is the path. So then this is the path. C to G, C to K. Here C from starting C, I started C, go to G, then go to K. This is the path of this line. Clear all of you? Next one is subtree. So A, then this is left subtree, this is right subtree. So then what are the tree elements formed in the left side? That is called left subtree, left subtree. Then what are the elements or nodes forming in right side? That is called right subtree. That is called right subtree. All of you. Next one, these are all the terminologies in the tree. Clear? These are all the terminologies in a tree. So then the next one is binary tree data structures. What is a binary tree? A tree in which every node can have maximum of 2 children is called binary tree. A tree in which every node can have a maximum of 2 children is called binary tree. So simply trees are 2 types, general trees and binary trees. General trees, then there is no limit. A node can have one 0 or one or more children. That is called general tree. Whereas in binary tree, every node can have a maximum of 2 children. That is called binary tree. Maximum of 2 children. For example, A have how many children? B and C, 2 children. B have how many children? D and E. So then D have how many children? H and I. Then C have how many children? F and G. F have how many children? Then J. So this is a binary tree. Clear? This is a binary tree. In a binary tree, every node can have either 0 children or 1 children or 2 children, but not more than 2 children. That is binary tree. So next one is strictly binary tree. Binary tree, there are 3 types. Okay, ma? First one is strictly binary tree. So strictly binary tree, here simply, so in this tree example, a binary tree in which every node has either 2 or 0 number of children is called strictly binary tree. For example, A here has either 2 or 0. A having how many children? 2 children. B and C. B having how many children? D and F, 2 children. D having how many? I and J. C having how many? G and H. Clear? All of you? Then this is called strictly binary tree. A node has either 2 children or 0 number of children. Don't use 1 children. Clear? So don't have 1 children. Either 2 children or 0 children. 2 children or 1 0 children. 0 children. That is called strictly binary tree. So this is an example. This is an expression tree. This is an expression tree. So this is a strictly binary tree example. This is also an expression tree. Next one is complete binary tree. Complete binary tree. In this example, so C does not have any children. So here we should fill elements in the C node, under C node. So for example, here left node and right node, that is called fully binary tree. So in this tree, all the leaf nodes are connected to children. So here all of you, then D have how many? 2. F have how many? 2. G have how many? 2. So then H have how many? 2 children. Clear? So this type of trees are called complete binary trees. Then complete binary trees. A node, a root node, or a parent node having 2 children, left and right children. That is called complete binary tree. A binary tree in which every internal node has exactly two children. Exactly two children, and all leaf nodes are at the same levels is called complete binary tree. All leaf nodes at same level, that is called complete binary tree. Next one is extended binary tree. We want to extend this. This is called extended binary tree. Clear? So this is a general. This is also binary tree. It is a binary tree, extended binary tree. Three types of binary trees. Clear? So next one is binary tree representation. So binary trees we will represent in two ways. The first one is array representation and the second one is linked list representation. Consider the following binary tree. This is the array representation, then this is the linked list representation. In array, so we should define one-dimensional array to represent binary tree. Consider the above example of binary tree and it is represented as follows. Clear? Next one is linked list representation of binary tree. So in the linked list representation, each node have three parts like double linked list. Each node have how many parts? Three parts like double linked list. The first part is the left child address. It holds the left child address. Then the second part is the data part and the right child. And next one, last one is the right child address. It holds the right child address. So clear? This is an example for linked list representation using binary tree. Binary tree using linked list representation. This is a data. This is node. This is node. This is that it holds the address of the left subtree. Then it holds the value of a. Then it holds the right side. This holds the address of the right side subtree. Same. All of you clear? This is the linked list representation of binary tree. Clear? Next one is binary tree traversal. So there are three types of binary tree traversals. What is tree traversal? Displaying or visiting order of nodes in a binary tree is called as binary tree traversals. What is binary tree traversals? What is traversals? Displaying or visiting order of nodes in a binary tree is called as binary tree traversals. There are three types of tree traversals. The first one is in-order tree traversal. Second one is pre-order tree traversal. Last one is post-order tree traversals. How many tree traversals? There are three kinds of tree traversals. In-order tree traversal, pre-order tree traversal, and post-order tree traversal. For example, this is the binary tree. This is the binary tree. All of you. So this is the binary tree. This is also a binary tree. How many nodes are there? This plus is a parent node. A, B are the children. A and B are the children of this plus operator node. Then A left node and B is a right node. A plus B. This is an infix notation. This is an infix notation. So I want to convert for example, I want to convert infix to postfix or prefix. What is a prefix expression? Pre means the operators are placed before operands. Clear? Here simply before pre-increment, pre-order traversal. Here plus A, B, plus first process the root node, display plus, then process the left subtree, then this A plus A, and control go to the right subtree and process B, then display B. Here simply what is a prefix expression? Plus AB, plus AB. Then what is a postfix expression or post-order traversal? In the post-order traversal, operands follows operators. Operands follows operators. First operands, next one operators. Clear? Then in this example, so here simply operands A first traverse or process the left subtree and process the right subtree and process the root node. Process the left subtree, process the right subtree and process the root node. Simply process the right subtree, left subtree, display A value. Then process the right subtree, display B value. Then finally process the root node, that is plus, display plus. Here AB plus. Clear? That is post-order traversal. That is post-order traversal. In this also, in this example, what is an in-order traversal? In the in-order traversal, what is a principle? What is a principle? Left to right to root. Left to right to root. First process the left subtree, and process the root, and process the right subtree. Clear? So in the inner traversal, in this example, what are the elements? So inner traversal I, D, J. So process left subtract. Then B, F, A. Clear all of you? Next one is C. Next one is K, C, H. Clear? This is the equation. Simple all of you. Here I, D, J, B, F, A. All of you. A, K, G, C, H. This is the inner traversal. K, C, H. K, C, H. Clear? K, C, H. K, C, H. No, K, G, C, H. That is an inner traversal algorithm. So next one is the pre-order traversal. Pre-order traversal. So left root to right to left root to D, I, J, B, F, A, K, G, H, C. Okay, ma. This is the pre-order traversal. Post-order traversal. So roots are lost. Here I, J, D, F, B. Clear? Next K, G, H, C, A. That is the post-order traversal. All of you. Then these are the tree traversal algorithms. Most important. All of you. These are the tree traversal algorithms. Most important. Learn. Then threaded binary. Today concept is threaded binary tree. Today we need to discuss threaded binary tree. What is threaded binary tree? A binary tree can be represented using array representation or linked list representation. When a binary tree is represented using linked list representation, the reference part of the node which does not have a child is filled with a null pointer. Clear all of you? In a binary tree representation, there is a linked list representation. The child node does not have any childs. Last node does not have any childs. Simply the child nodes filled with null pointer. Clear? The child nodes filled with null pointer. See this example, all of you. So then these are the child nodes. I does not have any sub nodes, but that's why this is called child node or leaf node. Then there is no link. Then there is no left subtree. Then there is no right subtree. Then node to left subtree equal to null and node to right subtree equal to null. Clear? Then this is the example for binary tree using linked list. Clear all of you? So whereas in a threaded binary tree, so then this null this node I node to right left subtree equal to then root node, then I node to right subtree equal to D. It is connected. That's why that is called threaded binary tree. Then there is no null value in the threaded binary trees. Clear? So all of you, I will explain. I repeat. So in the threaded binary tree, so whereas this is the binary tree using linked list representation. Whereas in the threaded binary tree, this node, I node to left subtree equal to root. I node to right subtree equal to parent node, that is D. Clear? Here J node to next, J node to left subtree equal to parent node, that is D. Then J node to right subtree equal to then FB. Clear? So like this. Then there is no null in the threaded binary tree. That is a threaded binary tree. Then there is a thread. So that is used to connect so previous node. Okay, ma, that the thread is used to assign the previous node address in the left subtree and right subtree. Clear? That is called threaded binary trees. Okay, all of you, threaded binary tree. Clear? The node which does not have a child filled with null pointer. In any binary tree linked list representation, there is a number of null pointers that actual pointers. Generally, in any binary tree linked list representation, if there are 2 to the power of n number of reference fields, then n plus 1 number of reference fields are filled with null. Here n plus 1 are null out of 2 to the power of n. This null pointer does not play any role except indicating that there is no link, no child. So clear? These authors said propose new binary. A say Perlis and C Thornton have proposed new binary tree called threaded binary tree, which makes use of null pointers to improve its traversal process. In the threaded binary tree, null pointers are replaced by references of other nodes in the tree. These extra references are called threads. These extra references are called threads. Threaded binary tree is also a binary tree in which all left child pointers that are null in linked list representation points to its in-order, pre-order, and in-order predecessor, and all right child pointers that are null. So in linked list representation, points to its in-order successor. If there are no in-order predecessor or in-order successor, then it points to the root node. For example, this is a binary tree. This is a binary tree. All of you. For example, then there is no child node of H. Then it connected to the root node. So what is an advantage? Whereas in binary trees, I want to move from H to a root node, so it is difficult. It will take some time. For example, I move from H to D, D to B, and D to A. Whereas in threaded binary trees, then there is a shortcut way. H2 that is connected to root. So no need to traverse these two elements D and B. It will go to direct. That is an advantage of the control go to the direct. That is an advantage of threaded binary tree. Clear? Clear all of you? So the convert above example binary tree into threaded binary tree. First node, first find the in-order traversal of that tree. What is an in-order traversal? HDI, BE, A, J, F, C, G. This is an in-order traversal of this given binary tree. Clear all of you? Then the next one, in-order traversal of the above binary tree is this one. So next, when we represent the above binary tree using linked list representation nodes, H, I, E, F, J, and G, left childs. What are the H, I, E, F, J? These are the leaf nodes. Leaf nodes. Child nodes. H, I, E, J, J. E, I, J, J. These are the left child pointers are null. This null is replaced by address of its in-order predecessor respectively. I to D. Where is I? I is connected to D. I is connected to D left childs. Clear? Then the next one is E to B. What is E? Here E to B. E is a child node. This is connected to parent node. Understand? Next one is F to A. Where is F? This is F. F2, F2 left, then there is no left child. So that is connected to A. All of you. Then left to, then G to C. What is G? This is G. Then there is no left child, that is connected to C. All of you clear? So here I does not have any left child, that is connected to D. E does not have any left child, that is connected to B. F does not have any, that is connected to root node A. J does not have any left child, that is connected to F. G does not connected to any childs. Then J left G to next equal to then C. Clear? This is threaded binary tree. This is called threaded binary trees. Here threaded binary trees. All of you. So another one. This is the another threaded binary tree definitions. Here we will see the threaded binary tree data structure. We know that the binary tree nodes may have at most 2 children, but if they have only 1 children or no children, the link part in the linked list representation remains null. Clear? Using threaded binary trees representation, we can reuse that empty links by making some threads. If one node has some vacant left or right child areas that will be used as thread, there are 2 types of threaded binary trees. The single threaded binary tree or full threaded binary tree. In a single threaded binary mode, threaded mode, there are another 2 variants. The first one is left threaded and right threaded. Threaded binary trees mainly three types. Threaded binary trees mainly two types. Okay, ma. So then, so two types. Use it. There are two types. Two types of threaded binary trees. One is single threaded tree or fully threaded binary tree. First one is single threaded binary tree or fully threaded binary tree. So the single threaded binary tree is also divided into three types. The first one is left threaded binary tree, and the second one is right threaded binary tree. Right threaded binary tree. All of you. This is an example. In the left threaded mode, if some node has no left child, then the left pointer will point to its in-order predecessor. Similarly, in the right threaded mode, if some node has no right child, then the right pointer will point to its in-order successor. In both cases, if no successor or predecessor is present, then it will point to header node. For fully threaded binary tree, each node has 5 fields. 3 fields like normal binary tree node. Another 2 fields store Boolean value to denote whether link of that side is actual link or thread. So this is the node. This has how many parts? 5 parts. Your data left link, right link, then left thread flag and right thread flag. So newly added 2 flags, that is the first one is left thread flag and right thread flag. So this is an example for left threaded binary tree. So see, all of you observe. So this is only one way direction. Here from 85, then there is no children. So that's why here 85 to left equal to root node. So then here 32 left equal to right node. Then here 22 left equal to header node. Clear? So these are this is an example diagram for left threaded binary tree. Next one is the right threaded binary tree. So here 12 child node. It is a child node. It does not have any right node. Simply child node to connect to parent node. Clear? Then this is also, it does not have any right node. That's why this is connected to root node. So it is also, it does not have any right node. That's why this is also connected to root node. So 85 does not have any value, right value. So that's why the right link connected to the previous parent node. Clear? This is the right threaded binary tree. The arrows indicated. So from right to previous, right to previous, right to previous, right to previous, right to header node. Clear? So then this is called right threaded binary tree. So this is the left threaded binary tree. This is the right threaded binary tree. This is the fully threaded binary tree. So 3 types of binary trees. Clear? Fully threaded. Then left and right holds the addresses of the header nodes or parent nodes. Clear? Root nodes or parent nodes. Left and right. Clear? Combination of left threaded binary tree and right threaded binary tree. Combination of left and right threaded binary trees is called fully threaded binary tree. Clear? What is threaded binary tree? So what are the types of threaded binary trees? Explain with examples. This is the most important question. All of you from 4th unit. Tree traversal algorithms and threaded binary trees. So tomorrow we will discuss next concept. So okay, ma. Tomorrow we will discuss the next concept. What is the next concept? The next concept is tomorrow maybe holiday. The next concept is balanced binary trees. Balanced binary trees and heaps, max heap, insertion into deletion from a max heap binary search trees. Okay. Tomorrow we will discuss balanced binary trees and max heaps. Clear all of you? Then okay, ma. All the best. Bye.